Okay. So the data set we have is an OpenAlex data set, which should be exactly the same format. When you retrieve them in the as a why it is not a service under definition. Okay, it should be working. Okay, so you get the data from somewhere, OpenAlex, and then these are the results. You should be very familiar with it right now, right? So import pandas, and then we get data. I already prepared the data here. So we have the data set like this. Specifically, I focus on the authorship here, the authorship, right? Authorship field will give you something like this. So like author position, institution, etc., ID, display name, etc. I will extract the author information from the author field and then construct a data frame with author ID, author name, and OpenAlex ID. The data frame will be used to construct a bipartite graph of author and papers. So they have a paper and they have an author. So, but for the bipartite network, it means in the network, there are two types of nodes. One type of nodes are authors. The other type of nodes are papers. That's called bipartite. For index in this database, you know, what I'm going to do is I'm going to iterate all the papers. So I have authorships. I extract all the authorships, and I have OpenAlex IDs, which represent the article, right? And then I have a temp, I have author ID, I have display name. I extract the author's ID, and it's the name of the authors. And then I add the author ID here, which represents the paper. So now what I have is, okay, here's the author, here's the paper. I can connect a line between the author and the paper. That makes sense? Each paper, every time if I go through the paper, I will be able to complete a part of the bipartite network, right? So I have authors. I put all the content here. The authors I concatenate, right? So these authors, this author data frame have all the information. It have two columns. You have two columns. One is about the author. The other column is about the paper, right? So if they appear in the same line, they indicate that. Okay. Next, if you see this is how the data frame look like. This is author ID, which is a unique ID of this author, and this is author name. I need to know who they are, right? So next is OpenAlex ID, which represents the paper, right? So I can draw a line from this author ID to this OpenAlex ID, which means there is a connection. They publish a paper like that. Next, what I'm going to do is I will construct a bipartite graph of authors and papers. Pay attention that I'm using the author ID, but not author name to construct the graph. The reason for doing that is because what?
The
same name, right?
Yeah.
Yeah, the same name. Disambiguation. Yeah, disambiguation. Yeah. The same author, even they have the same name, it does not necessarily means they are the same person. So when you do the network analysis, make sure while you are constructing a network, you are using their unique ID, not using their attributes. So here, the name of this author is their attributes, but not their. I'm not Jima. I'm my social security number, right? So even I change my name, change whatever I have, change my attributes, my social security number is still the same. It's still the same. So these are I add ages from this data frame. I got a bipartite network here. This step is critical. So analyzing a bipartite network is very, very challenging, both theoretically and algorithmically, right? Because you have to more advanced algorithms. Usually what people do is they will project, the keyword here is project the bipartite network to a unipartite network. So there's a function for doing that, which is quite intuitive, right? Project the bipartite network. So in the unipartite network, what I need is not a paper network, but an author network, right? So I define all these nodes need to be, I want to return all the authors from the bipartite. I want to project the bipartite network to a unipartite. But in the unipartite network, all the nodes should be authors, right? So that's why I'm using the author ID here. Okay. The algorithm know, so it will export a network of authors. So here I have all the authors here. So you see, I have all these attributes here. Okay. So you see, I have all these authors, these ID, right? All these are also unique IDs. Here. Next, I want to add attributes. So I add all the names back to the node, Now, if I show you again, it will be a little bit of different. Do you see that? For each node, I have a name section here. I have a name key here. Do you see that? Now each node, they are not empty. They have these attributes. The same rationale. Now I'm going to calculate the network measures and save the results as dictionaries, retrieve the results later to save time. So here I calculate, here are how I calculate all this degree centrality, colony centrality, between centrality, and eigenvector centrality, right? So I give them a dictionary, and then I set all these values to the node again. Let's take a look at what are the nodes looks like that right now. So you see, I have a node here. This is node ID, unique ID. I have a name. I have degree, 0, degree centrality, colony centrality, between centrality. All these attributes, they are the attributes of this specific node, right? I'm done with the analysis. I have all the measures here. In network analysis, remember the visualization and analysis, they are separate stages. Visualization, they focus on different things. The analysis is very computational intensive. The visualization is more like a rendering. It's more like a rendering, right? So they are focusing on different things. That's why a lot of the packages, they are good in one thing, but not the other. Like Python, the NetworkX package is good at calculating, but not good at visualization. Because visualization, you need JavaScript, which is more front end, right? So for Gephi or some packages like that, they use Java to render the visualization part, but they are not good at calculation. They are not, if you use them to calculate 5,000 nodes to get between this centrality, the program probably will crash. So that's, you have to separate them, right? The way my workflow is always, I will use Python to do some calculation, and then once I got the number, I set the number to the node, and then I export it as a network. Here I have this graph ML here, something like this. You see this before, right? Like I have a node, I have a key, data key. I have like you see, I have between the centrality as a data D4, data key D4. And then I have other keys here. This is the first node, right? Data key D0, D1 is 0. What D1 is? D1 is this degree, right? It is 0. D2, what D2 is? Degree centrality. What D3 is? D3 is colony centrality. Every node is the same. Every node is the same. And I also have edges. If I scroll down here, there will be edges from source, from target. But because this is an undirected graph, yes. It will probably some undirected here. So it is undirected graph. So the target and source, that makes sense. They are meaningless in this sense. Okay, I have the graph here. Next, what I'm going to do, I will download this graph. I will get this graph somewhere, and I'll open it with Gephi. Download. Okay. Now let's open it.
There's also a way to export the Gephi put it on your website and as a JavaScript.
Ah, oh, on website.
But it has to be as an add-on that does it.
Ah, okay. That I don't know. View details. Let's find this graph here. Okay, they give you a summary of the, there are 12,000 nodes here with 27 edges, right? So click OK. I won't surprise if we see a mess. Yes, overview. I think it is, we need to go to the overview here. Preview is somewhere you want to export them. It's not beautiful, right? It's not beautiful. What do we need to do according to what we discussed earlier? Do some pruning, right? Do some pruning, right? There are many ways to do that. Let's use attributes equal. Let's use depending on research question, right? So if my research question is I want to find out the brokers in the network, so I want to disregard all those nodes with very small, like the degree centrality, between centrality here. So parameters, let's take a look. Oh, the value is just too small. Filter. Yeah. 0 point, no. Range match, column between centrality. Degree, let's try degree again. Oh, okay, that's too much. Let's remove all this again. Remove, okay, between centrality here, we remove it. We use degree. So the degree here is minimum is 0, which means these are isolated node. They are not connected with anyone. So we can't ignore them because they are not connected, right? So let's set it is as 5. 1, 2, 3, 4, 5. Okay, filter. Ah, that's too many, right? That's a 3. 3 looks good. 2. If I say, okay, that's just too arbitrary, right? Which number you should use? Of course, for showcase, I'm very subjective. But every time you want to do is they need to be justified. But for now, let's just use this. And there's also another commonly used way called K-core. K-core. I think it is probably partition or something.
You can also do a dynamical graph where it evolves over time.
Yeah.
But you need to have the data.
Yeah, exactly. You can use K-core as well. Oh, I mean, or you can use K-core as well.
Okay. Cool.
Yeah, I mean, I'm not following what you just said. You just say it right, but it's about dynamic. But we don't have a dynamic here. No. So K-core is a very commonly used way of pruning. What K-core is I can give you a quick example here. Yes, we do have time for the example. We have node here. Okay. For k equal to 1, it will erase all the nodes with only one connection. So in this graph, which node should I get rid of? This one, right? Because this one only have one connection here. Oh, okay. So next, if I use k equal to 2 as a criteria, which means every node only have 2 connections will be removed from this network. So which node will be removed? This one. You see that? This node have 2 connections here. So it's gradually exposing the core, depends on how you define. Core of the network, this area, right? You see that? Equal to 3, I will remove all the node with only 3 nodes there. So this kind of very it's used very often in a lot of analysis, and usually people will use k equal to 3, but depends on the network you really have, right? Sometimes you probably will also want to visualize, also want to show people the distribution or the proportion of how many nodes you proved, how many nodes you retain, right? So give people a sense about the overall picture. Okay, now we have a less messy network. It's not beautiful. Do you see all the layout? We talk about layout, right? We can use the layout. These are all algorithms define how this network will be visualized. Let's use Force Atlas. Try to see what it will look like. Okay, it will look like this. If we use the Ringgold, it will like this, right? Is that? So these are all the algorithm. This is not some attributes, not some kind of attributes of the network itself. There are separate algorithms. We can use other. Probably let's use expansion. Yeah, or just the expand. Expansion, just expand. Force Atlas 2. Next. So it will converge. I think Force Atlas 2 is an algorithm which will make the clusters more apparent. So if they cluster together, it will make all those clusters more apparent. So different algorithms have different purposes. Depending on what you want to visualize, you can choose different algorithms, layout algorithms. For this one, let's just choose this Rango here. So it will be something like this. It start to become a kind of network that is risk-taking. Let's take a look. Yeah, we will have more. We don't have modularity here, partition, which means we want to cluster them in different groups. We can run some analysis here because we only have very few nodes here, so it's not a problem. Let's run the modularity, which will give us the modularity class. So 80% that belongs to 0. Now let's apply. They will give you some color here. Next, we want to change the size so that larger node are more apparent. Let's use degree centrality. The max size, I want to increase the contrast. The max size I will give to 20, and then the smallest I will give to 4. Still not that appealing. Let me see. Let's use 50. Still too small. Yeah, this is a very disconnected graph. Let's try another measure here. Use degree. Oh, it's a very disconnected graph.
Did you run average degree?
Average degree. That's the same. I already calculated because I use Python. I already use Python to calculate it, right? Yeah. So I already have the numbers here. The reason I have the numbers here is because I don't want to do that again. Okay. I think it's yes. The reason we are getting all this kind of not appealing graph is because we already prune it. So sometimes the calculation can do before pruning and after pruning, right? So if you do before pruning, you get results. So which means they will calculate all these numbers, calculate degrees with all those nodes, right? But if you do the after pruning, it will calculate all these numbers without all these nodes, right? So we are seeing a graph which is not good. So we will do it again and see what we can get, right? Okay, let's remove this filters here and run some numbers again. Run modularity again. And then let's do the, we already have the degree here. Yeah, let's redo this. Let's make it faster. Okay, so we have the click here, click here, click here. We have a lot of clicks here, right? You see that? Next, we want to visualize them according to their modularity. We already run the modularity class. Not ranking, it's a color. Modularity class, color. I want to change some color. Let's do the largest full. Apply, okay. Looks like something, right? So especially this area. I like this area. I like this one, right? It's like they are scattered around, but still they have some high connected figure here. These are more like very condensed clicks. Very condensed clicks. Size, ranking, I will use degree. Let's see what we can get. Tune it a little bit. How about use betweenness? Oh, okay. Look, we have some differentiation here. Like this node is like a brokers here. This node is broker here. This node big broker. This is another broker here for these different camps. So the node size represent the betweenness or the brokerness, right? How important they are in this network in terms of their boundary spanning roles. Next, we still want to know what they are doing, who they are, right? Next, very intuitive, who they are. This guy. Open the label. It will become very messy because we haven't doing a lot of things yet. So we want to choose the nodes label as name. Looks good, but all these labels, they are the same size. You see that? We want to make like some of the nodes, they're probably very small. We want to make those non-important ones small. So there's a trick you can do. You can scale the node size with node size. You can scale the label size with node size. We get something much better here, right? You see that? We get something much better here. Okay, we need more magic here. So let's do label adjust. Look at that. Now we see all these names clearly. We see all these names much clearer. Do you see that? Probably the non-overlap. Okay, give us a better sense about who are these people in a network. Okay, regarding network, this person probably will be very important in terms of bridging people, scholars from different fields. This person is also important. And this person, these nodes here are very important. You see this huge click here. Do you see that? There's no one very important for this click. It's probably, I would say it's probably just one paper with a lot of co-authors, right? So they themselves form a very small society. They're not collaborating with a lot of people there. So you probably, depending on your question, you probably want to look into them, or you probably want to see how these people are really connected. So the widespread connection about them. Now, we want to see all them clearer. So what we can do is let's keep doing the k-call. Let's try k-call. K-call here. Let's use filter 2, 3, 4. Okay. Now we have all the nodes here. And we can rerun the algorithm again. So all these nodes, because we already removed, but they're still, the space are there, right? We rerun this algorithm again, so they became close to each other. And then we also do label adjust, do non-overlap, so that they do not overlap, right? So this is a graph we got. If you want to export the graph, we need to go to preview. Let's refresh quickly. So we have a node like this. Sometimes people like curved, some people don't. I usually don't. Yeah, in the early years I use curved, but then I see it's actually doesn't add too much information there. So I'm not using curved in recent years. Node node labels. I will show labels, refresh and see what we got here. I want to change the font here. Times New Roman. This probably refresh again. Okay, we got this. You can change the border, change a lot of things. There's a lot of things you can play with. I will skip for the time, for the sake of time. So you got all this figure here. Now you can export it either as a SVG, PDF, PNG. Usually you want to export all these files as a vector file. You know, there are two types of file, raster file, raster file, and also vector file. Vector file is a high resolution. It's very clear. SVG is a vector file, and PDF is vector file too. Usually I just do a PDF. PDF is good enough. Yeah. Yeah, that's the overview. So you see calculation, visualization, they are separate. If I rely on Gephi, help me do the calculation, it will crash probably. It will spend a lot of time. So Gephi is very good in terms of visualization. It gives you a appealing graph like this. You can keep removing all these nodes until you really have all this. I think this is probably the click and all how these connected are very interesting to me. The rest of the like this disconnected, like this click is disconnected. Yeah, here. This is disconnected click. I probably want to remove it so that I want to study. You still require, there's a called the largest connected component, right? So I would say all these colors, they are probably the largest connected component. And this one is the disconnected component. So I will remove the disconnecting component and only analyze the largest connected component in the network. Yeah, because I want to analyze quote unquote the mainstream. Yeah. But if you want to compare the marginalized or those isolated component and the quote unquote mainstream, that will be very interesting as well, right? Because for the from the research perspective, which is interesting to compare as well.
If we want to exclude the unimportant networks here, can we authorize it on Gephi or we have to go back to the Python?
You want to do what?
Like to exclude this unimportant network.
No, you can use Gephi. You can use Gephi. Yeah, you can you know, I think there's a way you can just directly exclude them by selecting them. Yeah, I guess so. Delete, right? Delete. You can also label them. If you go to Python, for example, I can create a separate column. I will label exclude, include, right? I'll create a separate column with two values, include or exclude, right? And then here, I will just do you see all these attributes here, right? So I will choose attributes equal, like let's use modularity class, right? So equal, there are different modularity class here. I will just choose one of the value, and then I can filter them. Yeah, filter them. It takes some time. It takes some time to really make everything smooth. But it's very interesting to play with it, especially if you are working with a data set that is on a topic you are interested in, right? So because you want to know these guys, you want to know what they are studying, and you want to know their relationship, right? Because their relationship is an intellectual relationship, because these are the backend behind the knowledge generation. There is one ongoing working project, a working paper I'm doing right now with another economist. So in the United States, there's an agency called Council, CEA, Council of Economic Advisors. Usually there are 3 persons who will draft the economic report of the president. they directly provide evidence to the economic advice to the president since 1940s. They will write a report and they will cite a lot of knowledge. Our research question is like this. So what's the social structure and scholarly structure for generating knowledge, for presidential decision making? So on whether this kind of a social network or this kind of a scholarly network have some characteristics in terms of Biden administration, Trump administration, and Obama administration, right? So each of the presidents, what kind of knowledge they are using, and how the knowledge was generated, and what's the scholarly relationship about that knowledge base for the presidential money making. That's a very interesting working paper we are working on right now. That's it. Any other questions? Okay, I will post this recording somewhere on Canvas or probably just share